All right, so we're now looking at not just the e to the x function. We did that yesterday, and the surprising thing about that function we found out was that the derivative of e to the x was e to the x. Right? That's a little unusual, but that's the way it is. The derivative of the function is the function itself. But what about when the base is not e? And by the way, we talked about what e was. It's this very special number in math, which I used to be fascinated with at one point when I was trying to differentiate x to the 1 over x. I talked about that yesterday. And if we have some time, we'll actually go back to that and show you how you can differentiate it, because I couldn't figure it out at one point in my math career. Anyway, the derivative that we're going to look at today is not for the e to the x function, but the a to the x function, meaning what if the base isn't e? What if the base is some other number, like 5 or 10 or 15? Then what do you do then? All right, so if f of x is, one more thing before we go any further. If you're, as we go through this, thinking, oh my God, there's so many rules that we have to learn with derivatives, not to worry. There is a handout on the Math Video Library, which you are entitled to use and you're allowed to use on a test, which gives you all the derivative rules, right? If I was still on the website, I would show it to you, but we have to move on at this point. But all the rules that the one we're going to be doing today, those are all on a handout on the Math Video Library. Nobody needs to commit it to memory. So the product law is there, the quotient law is there for logs, for exponents. Later on, when we start working on trigonometric functions, those are all going to be on that sheet. Okay? So don't have to commit it to memory. What you have to do is to know how to use them. All right, let's get to it. F of x is equal to a to the x, where a is a positive constant, so no negative constants, no zeros. Then the derivative of the f of x function is the function itself, so that didn't change, okay? But then you also have to multiply that by the natural log, base e log that is, same key on your calculator, the natural log of the base, a, for all real values of x. Let me say it again. So just like how we said e to the x yesterday would be e to the x, well, the derivative of a to the x, where a is some other number apart from e, is equal to a to the x, as I'm pointing to here. But then we have to multiply that result by the natural log of that base of a. So for instance, what does that mean? If I had f of x is equal to 2 to the power of x, then the derivative is 2 to the power of x, again, multiplied by the natural log of 2. But the natural log of 2 is some decimal number, right? It's some number. It's not, it's a constant. It's some, it's whatever that, just remember what a log is. A log is an exponent. So what it is what do you raise e to get 2? That's what the log, natural log of 2 really means. So there you go. It's very similar to yesterday, but now we have this other part of it, which is to multiply the result by the natural log of 2. So let me take you back to yesterday for a minute. Yesterday we said that if you had the function e to the x, the derivative of that would be e to the x. Now you can see why this function, this way of deriving things makes sense, because I would do this. I'd say e to the x and then multiply that by the natural log of e. Well, the natural log of e is 1, okay? If you're taking the base 2 log of 2, that answer is 1. The base 3 log of 3, the answer is 1. So the base e log of e would also be 1. If the base matches the log that you're taking, then it means that you're always going to get 1. So this is really just to point out that we were doing this all along yesterday, but we just didn't know it. It is the e to the x multiplied by the natural log of the base of e. But in the case of e, because the natural log of e is 1, it didn't change it. It's still going to be e to the x. Okay? Pretty straightforward, hopefully, so far. And that's why it just works out to be e to the x, because that 1, this ln of e being 1, makes it just e to the x. Okay. On the other hand, yesterday we learned that if the function was the ln of x, then it was 1 over x was the derivative of that. Again, that will be on the sheet that you could use. That was what we learned yesterday. But what if it's not a base What if the log that you're taking is not a base e log, which is what ln means? What if it's some other base? Well, if it is some other base, like base a, then the f prime of x, which is the derivative, is going to be still 1 over x, but that x is going to be multiplied by the natural log of a. All right, so notice that this is in the denominator this time. So it's 1 over x, but times the natural log of a, whatever that base is. So if the base was 5, so let's say this, okay, let's say the base was 10. So if f of x is equal to the base then log of x, then the derivative of this would be 1 over x times the natural log of 10. It's as simple as that. Really as simple as that. Here comes the first example, right? 3 to the power of x. So the base here is 3 this time. Okay. So if that's the case, my dy dx will be equal to 3 to the power of x times the natural log of 3. There you go. All right? Couldn't be easier. As we said, you still have the 3 to the x, but now we have to multiply by the natural log of whatever the base is. That's all it is. Okay? Here's another example. And we're going to sort of tackle this two different ways, which you'll see in a second. If we have 4 to the x times 5 to the x, think about that for a second. So it's a product of two functions, both of which are exponential. Right? 4 to the x is exponential, 5 to the x is exponential. And we're multiplying those two things together. Result of that would be as follows. Using the product law, I'd have this part here, the first one, derived, which would be 4 to the x times the natural log of 4, because that's what we said we do for derivative, times the underived second part, that's the 5 to the power of x, plus, just using the product law, the same procedure again, the 5 to the x times the ln of 5 times the underived first part. Now, can this be simplified? Does anybody see any way that we can simplify this? Look at that. Look at that. Look at what you're looking at right now. So 4 to the x times the natural log of 4 times 5 to the x plus 5 to the x natural log of 5 times 4 to the x. Is there any way to simplify what we're looking at here? Come on, folks. Before I click that mouse again, do you see any way that this could be simplified in any way at all? No simplification possible. I'm sure there is. Can you see a way that we could put like terms together, factor, anything at all? Add the, let me see what Fernando is saying now. Add the 5s. 5s. You mean 5, what's 5s? Oh, the fives. I see what you're saying. Add the fives. The fives. Oh, I got you now. Yeah, I don't know why I couldn't think of that. Well, sort of. What we should be thinking is, isn't there a common factor between both of these? Right? Isn't there a common factor between, there's a 4 to the x here, there's a 4 to the x here, there's a 5 to the x here, there's a 5 to the x here. Isn't there a common factor? Okay, so Kushi is saying take out 20 to the 2x. 20, when you say, okay, I'm not sure where the 20 is coming from yet, but here's what I'm seeing as my common factor. There's a 4 to the x here, a 4 to the x here, a 5 to the x here, and a 5 to the x here. Isn't that your common factor then? 4 to the x and 5 to the x? And then when I factor that out, am I not left with ln of 4 plus ln of 5? You see where I'm going with that there, folks? Right? The common factor is these two. Let me grab my stylus here. This is the same as that. This is the same as this. They're both part of these two terms, right? So they would be both regarded as common factors. If I take those two out, I'm left with the ln of 4 plus the ln of 5. Does that make sense before I go any further? Does that step make sense if I factor those two things out? What do you think, folks? Okay, good. Now, you need to remember all the stuff we learned about logs, not just in this course, but in previous courses. These two things here, I can combine them. The log base a of x plus the log base a of y is equal to log base a of x times y. That's one, right? So it looks like I can combine these two here, right? By talking about the ln, and by the way, because they're both ln, I can combine them. Since they're both a sum with the same base, I can make them into a product. The other thing is, if these two things, 4 to the x and 5 to the x, if it had been that I had them as, and I'm just going to show, I point them out to the most. I don't need to read it right on the thing. These two things are both to the power of x. Why not just combine them both and raise them to the power of x? Because this is an exponent which has to be distributed inside the bracket, so I can now regard it as this. This is 20 to the power of x. And these two can be combined as being the ln of 20. Okay? I want to be sure people see what I just did there. These two can be multiplied together, because if I have a to the power of x and b to the power of x, I can multiply the a and the b together and raise them both to the power of x. Right? So that's why this is 20 to the power of x right here. The ln of 4 plus the ln of 5, I can also combine both of these to give the ln of 20, because that's one of the logarithmic rules. It's the product law of logs, that a product can be written as a sum. So this is my answer. But I want you to notice something else. This original question, just as how I could write 4 to the x times 5 to the x as being 20 to the power of x, I could have written this original question as 20 to the power of x up here. And if that was the case, then my answer for taking the dy dx of that would be exactly the same as this thing right here. It would be 20 to the power of x times the log, the base n log, the base e log, sorry, the base e log of 20. So this answer that I'm getting is consistent with just simply differentiating this piece up here. Okay, hopefully that makes sense. Okay, let's do this one. 3 to the power of ln x. Well, it's another function of a function. And by the way, stop me, ask me to go back if anything doesn't make sense. Don't sit there passively, sort of just looking at the screen if something doesn't make sense, right? I'm fine with going back. What I'm not fine with is when you don't get something and you don't say anything. Okay, 3 to the ln x. So think of this as a function of a function again. So I'm going to go first of all and say this would be equal to 3 to the ln x, ln of 3, remember take the ln of the base, multiplied by the derivative of the ln of x, which yesterday we talked about as 1 over x. So these three things have to multiply together, right? It's 3 to the ln of x, so we simply repeat the exponent, the exponential part of the function. Then we multiply that by the ln, the natural log, the ln of the base of 3. Then we multiply that by what the ln of x is as an exponent, which is 1 over x. Another way of writing that is just put everything over x, right? Because these things are being multiplied over x. All right, so I'm just showing you a couple of derivatives that you need to be able to do yourself. Can you repeat that, Mr. Kamak? I sure can, Taj. So all I did, mean just the last part or the whole thing? I want to be specific here. The whole thing? Okay. So, all right. So think of this as being like y equals 3 to the power of u, where u is equal to ln x. Okay? So what I'm going to do is, I'm going to first of all find the derivative of 3 to the power of u. So dy du in other words. So dy du would be the same thing as 3 to the power of u multiplied by the ln of u. That make sense? So far? Is that part? Okay. But I also have to find du dx. And du dx, that's the derivative of this thing here, is 1 over x, what we did yesterday. So I have to multiply my dy du by my du dx. So that's why I end up with all of this. So it's the 3 to the ln x, 3 to the power of u, right? 3 to the ln x, times the ln of u, so that's the ln of 3, times 1 over x, because that's what the last part of that is. Does that make more sense now to you, Taj? All pass, Alicia says. Okay. Okay, Alicia, so expect you back within 5 minutes. 1:56 right now. Okay. And all I did for the last part, by the way, is just put the x on the bottom because it was 1 over x times everything else. That's all I did with that one. Okay. All right. And Taj, thank you very much for asking. And I want you to be the Tajes of this class, right? Something doesn't make sense, you say, Mr. Kamak, I need to just kind of look at that again. So I appreciate that, Taj. Appreciate that very much. All right, let's see if we can answer some actual questions now based on this. There are lots of exponential events that take place in the real world. Unfortunately, one of them was the growth of the coronavirus at one point. But, and that's why I don't know if you ever heard of talking about the R naught. R naught is really the base of that exponential function. R naught was how many people one person would infect. And when that was over 1, it meant you had an exponential growth function. And if it was less than 1, then you had an exponential decline. So if the R naught, and you may have heard that expression before, if the R naught is less than 1, then things are good because we're on a decline. If the R naught is more than 1, then we're unfortunately on increasing number of cases, that kind of thing. Anyway, let me get to this. January 1, population of Gold Rush Town was 50,000 people. Size of the population can be modeled by, and they give you an exponential function that represents that town, the number of people in the town. We're teasing the number of years since January 1 and 1850, and then they ask some other questions. Can I ask you this question before we go any further? Would this, oh, sorry, didn't mean to do that. Let me go back. Didn't mean to put the graph. The graph in there doesn't really matter. Let me ask you this. Based on what I just said about the coronavirus, look at that equation. I wonder if I can underline without revealing anything else. There we go. Does that represent, and you know what, the graph is kind of giving it away anyway. Is it an increasing exponential function or a decreasing exponential function? Okay, so you've seen the graph, so you kind of know that it's a decreasing. Why is it decreasing? Does anybody know why it's decreasing? What part of that function tells you that this is a decreasing exponential function? The 0.98 is less than 1. That's right. The base is less than 1. Thank you very much. That's that same R naught I was just telling you about. So this would mean that the population of this town is actually falling over time, which is what we want the case count to do. But this represents exactly that. The Gold Rush Town population is falling at an exponential rate, and we can figure out what the population is at any point in time by just simply putting it into this function. So here's the first question. What's the population of Gold Rush Town on January 1, 1900? Well, that's just simply putting 50 as our exponent. Why 50? Because 50 is the number of years since 1850, right? We're talking about in 1900. Just simply put 50 into the function, and that gives us this many people. So the town started off with 50,000 people. 50 years later, you're down to 18,000 people. Oh dear, right? Clearly, it's a town that's shrinking in terms of its population over time. And that's because, yes, the base of this exponential function is less than 1. Taj said it best. Thomas also agreed with that, and so did Sarah. All of them are showing that once the base is less than 1, you're going to have an exponential decline as you go along. If it was more than 1, 1.2, 1.3, that would mean exponential growth. Okay, so let's keep going. The first part is easy, right? We didn't need calculus for the first part. What's the population 50 years later? Plug 50 into the function and you're done. Let's get to the second part. At what rate? Okay, so now we might need calculus because every time we ask about rate, right, it's like an IROC kind of thing. It's a slope kind of thing. At what rate was the population changing on January 1, 1900? So when they had these 18,000 people, right, at what rate was the change? Well, let's now use the calculus to figure that out. It's a rate. It's a slope of the function at the 50 mark. So it would be somewhere around here where I'm pointing. We're really trying to figure out what the slope of the function is right here, right? What is, if I put a tangent line right up against the graph, what would the slope of that line be? Would you expect it to be positive or negative, by the way? Give me some ideas on that. Should that slope, that line that I'm putting there, be a positive slope or a negative slope? Absolutely, Adam. And one of the reasons for that is because this is a declining function. The function is decreasing. And we know that when we take derivatives of a function that's decreasing, it's supposed to be negative. Okay, so let's keep going here. Let's keep going. Let's first of all find the derivative of the function, right? And it works out to be this, 50,000 times 0.98t. So again, we don't change this at all, the original function. Let me come back to the original function. It's the same function, but then we multiply by the derivative, sorry, the natural log, the ln of the base of 0.98. So there's your derivative. So, Aisha, thank you. So what do we do with that now? Right, we have our derivative. What exactly do we do with that derivative? What is the derivative? How do we use that derivative to come up with the answer to the question? What's the rate? At what rate is the population changing on the 1st of January 1900? I have a derivative. What do I do with that? All right, I'm just going to throw it over to the class and ask you to tell me. I'm not clicking that mouse until you tell me what you think is going to happen. Or what do you think I need to do? Plug in the 50. So I'm going to set it equal to 50 or just plug in 50 for t. Which one, Ashvan? And which one, Richard? What do you think? Plug 15 for t, Ashvan says. Absolutely. So we just simply plug in the 50 for t. And if you have your calculators close by, it's a P1 of 50, or P prime of 50 rather, you will get this answer. And it says people per year because what's happening is that on that particular day, this town is losing people at the rate of 367. Okay, so there's no 0.86 of a person. Okay, so before anybody points that out, let me just acknowledge that. You can't have 0.86 of a person. But it is showing you that based on the projection model, you are losing this many people per year at that point in time. Okay? So the population is declining at the rate of 367.86 people per year, unfortunately. Okay, so that gives you an idea of how we can use derivatives to answer questions about the rate of change of exponential functions. All right? Okay, you know that we talk about half-life all the time. Radioactive material decays by 20% each year. The original mass was 100. How fast is the substance decaying at the instant when exactly half of the substance remains? That is after one half-life. Okay, so can we come up with an equation that represents this 20% loss? You know you're going down by 20%. So can I come up with an A equals something? Can anybody think of what that equation might look like if you're losing 20% each year? 100 times 0.2? Not quite 0.2. Not quite 0.2. You're close. Tash says 0.8. Yeah, absolutely 0.8. Because what multiplying by 0.8 does, Adam, is it takes off that 20%. Every time you multiply by 0.8, so every year you multiply by 0.8, you're dropping 20%. So, you know, when you go into a store, let me give you an example of this. If you go into a store and the sign on the front of the store says, you know, big sale going on today, 20% discount. If you want to know what the price of that item is after the discount, multiply the original price by 0.8. So there you go. So here's my equation. 100 times 0.8 to the power of t. T, of course, being time in years. So now we're asking, how fast is it decaying? Oh, sorry. Oh, I didn't know I could do that. I just wheel the mouse the other way, it goes back. Interesting. So that means that if I wheel it this way, it goes forward. Oh, I guess I learned this. I just learned that a while ago. I didn't know that. The little wheel on the mouse actually can control going forward and back on the PowerPoint presentation. All right, you learn stuff as you go along. Okay, so there's our equation, right? And we're trying to figure out what is happening when it's exactly half after one half-life. So where are you after one half-life? Well, you're at the 50 mark, right? That's 50. So what I'm going to do is I'm going to say set this equal to 50, right? Because I want to know when this happens, right? At what time? And then after that, we can use that time to see how fast it's decaying when you're exactly at half. How do I solve this? I set it equal to 50, right? How do I solve for t? Does anybody know how I can solve for t on this one? Right? I'm trying to solve for an exponent. Think back to your advanced functions now. It's something you would have learned in advanced functions. How do I solve for t here? We have to use logs, right? We have to use logs. Now, do we use natural logs or do we use regular logs? Does anybody know? Or does it matter? Does it matter what base of log you're going to use to solve this? Anybody? Anybody know? Remember, on your calculator, you have two types of logs. You have a base 10 log, which is just your regular log key, and a base E log, which is a ln key, ln key. Do we know which of them we should use for solving? Kushi said it's a log equation. I agree. Do we know how? You think it's a regular? It actually doesn't matter, okay? As long as you're consistent with it, right? Well, first of all, we're going to, of course, divide both sides by 100. So we do that. And now I'm going to take ln, right? Do I have to take ln? No, I could use regular logs as long as I do the same base on both sides. But since we know we have to use ln at some point, then I'm just going to go ahead and use ln, right? The truth is, you could use any base you like, right? Base 2, base 5, base 10, base 15, base anything you like. As long as you're using the same base on both sides, it doesn't matter. So I'm taking the ln of both sides because since we're kind of using ln anyway, I'm just going to go with ln, which is base C. And then if I take the ln of the two sides, which I'm doing here, I can use what's called the power law of logs to put the t in the front, and therefore t is equal to ln 0.5 over 0.8. So whatever this is going to tell me what my t is, right? So now I need to figure out, no, and I don't really want you to work that out. It doesn't really matter seriously, right? But we now know that when t is this number, right, this is the point at which you're going to be down to half of where you started off from. Okay. They want to know, at that point, how fast is the substance decaying? So now we need to know rate. So for that, we need calculus. So I'm going to find the derivative of the function that we have right here, that I'm pointing to right here. So it's going to be 100. By the way, this 100 in the front, just treat it like a coefficient, right? You can always derive the stuff that you need to derive and then put the 100 at the end. So it's going to be 0.8 to the power of t times the ln of 0.8, ln of the base. Exactly what we've been talking about. And what I'm going to do is I'm going to put in that time that we said we wanted to find the rate of change of this substance at. Now, I didn't put it in because I want to be as precise as possible. I didn't actually work out what the ln of 5 over the ln of 0.8 is, or 0.5 over 0.8. I'm just going to put that in the function as it is. So I'm going to put that in as my t value into the derivative function, Okay, so what does this work out to be? Minus 11.2. And in terms of a rate, it's decaying at the rate of 11.2 grams per year. So at that point, the slope of this line would be a slope of minus 11.2. And that means I'm losing mass, I guess. Yeah, mass. I'm losing mass at the rate of 11.2 grams per year. That's all it is. Okay. I think we have two other questions. And if we can get to, oh, no, we have one other question. Is it really the case? Yeah. Okay. One other question. And then we can probably try some of that stuff on the University of Waterloo website. So I wrote this one myself, and I don't have any preset answers for this. We're going to work this one through. So let's just think about this now. So James, lucky guy, hit the lotto, won $1 million, and he decides he's going to put this into the bank. Right? He's a smart guy. He doesn't want to go and blow it on, I don't know, a nice fancy car, maybe a Tesla or something like that. He decides, all right, I'm 25 years old now. This money doesn't last forever. If I put it into the bank at an interest rate of 5% compounded annually, at some point, by the way, I love doing money questions. I'm not going to apologize for that, right? That's something when I teach the finance unit in grade 11, that's my favorite time of the whole year. Anyway, let's keep going. Let's keep moving here. So anyway, he puts this $1 million in the bank, getting 5% per annum. And I must tell you, I must warn you that 5% right now is a very generous rate given the current economic environment. Since we're talking real stuff here, in the current economic environment, it's going to be hard to get 5% on any deposit, right? You're probably more likely to get like 2 or 3%, if that much. We're in what's called a very low interest rate environment right now. There are times when interest rates will probably get back to like maybe 5% and even more, but right now 5% is actually a little bit high. But we're just going to work with 5% for this question. So anyway, this James gets his $1 million lottery winnings and puts it in the bank at 5% because he figures that he doesn't want to touch it for now. He's only 25 years old, so I think it can work for a while. And he plans to retire at the very moment that his investments start earning $100,000 per year. So he's thinking $100,000 per year is a pretty nice salary. If my money that I'm putting in the bank, I'm not going to touch it at all. If it gets to a point where it's just spitting off cash at least $100,000 per year, and the way compound interest works is that it starts off pretty slowly, and then it sort of builds as you go along, right? So he's not going to get $100,000 in the very first year. So think about it. It's a 5% return. 5% of $100,000, of $1 million is not $100,000. But over time, according to this function here, which is a compound interest formula, over time, his investment will start spinning off at least $100,000 a year, and in fact, will even get beyond that. But he's saying, okay, I'm willing to wait until it gets to $100,000 per year. That's a pretty nice salary, and then it's even going to get bigger than that. I don't even have to touch that $1 million. That $1 million is going to sit there in the bank and just start spinning off the interest, and I can therefore sit back and stop working when it happens. Not going to be in the first year. Now, let me be clear on that. Not in the first year. This is sometime in the future. Obviously, the higher the rate is, the faster it's going to happen. But let's just say he is content to work for a while. He's starting at 25, just graduated from university. Let's just use that as a scenario. And he's prepared to work for a while until his money generates enough steam using the compound interest that he's earning, till he gets to earning $100,000 per year just in interest alone. He's not touching that $1 million, right? How old is he going to be when he retires? He's going to retire as soon as it hits that 100,000 mark. So I don't have the answer set out like I have for the other stuff that we've done. Can anybody tell me how you think we should approach this, right? I want to know when he's going to be at the point where his investment is generating, just on the interest alone, $100,000 per year. Now remember, it will get bigger over time. Find t at the rate of change equals 100,000. Okay, so you're on the right track. So how do I start that? Because remember, this equation now is just giving me the amount, right? If I want to know the amount of money in the account, then I just simply put in the value of t. Let's say I want to find what it is in 3 years. I put t as 3, and it tells you how much money I have. Set the derivative equal to 100,000. Okay, so why don't we try that? Because that sounds about right. That sounds about right to me, Tajan and Stephen. Set the formula equal. So I set this formula equal to 100,000 though, then solve for t with a log. So is it the formula that we're looking at right now? Yes? No, it's the derivative of the function, because we're trying to get the rate of growth of the investment. So we should find the derivative. Does that make sense to you, Stephen? I just want to be sure that we're clear on that. Not just set, because if you set this equal to $100,000, the truth is that you're going to get a negative value, okay? Because it's already $1 million, and you're asking, when is it going to amount to $100,000? Well, you just stole $900,000 from this guy if he starts off with $1 million and he's now down to $100,000. So I wouldn't do that. I wouldn't do that. So we're looking at the rate of growth of the function. So we need to find a derivative for this function. Okay, I'm going to sit back now and wait for one of you to put that derivative, because there is no answer here. I'm not going to, if I click the mouse, it's not going to give me an answer. That's not going to happen on this slide. I want to find what the A prime is, right? What would that, one of you put that, not one of you, I'd like to see several of you put that derivative in the chat right now. What would that be equal to? A prime. So the 100, give me what Adam has. So 100, actually a million. A million times 1.05 to the power of t times the ln of 1.05. Well done. Well done. So 100, sorry, 1 million. 1 million. Actually, don't know how to erase this. Don't know how to erase that. 1.05 to the power of t multiplied by the ln of 1.05. Can we agree on that? Thanks for typing. Okay, Kushi says, no problem. All right, can we all agree on that? Does that, first of all, derivative make sense? Perfect, perfect. Remember now, he wants to retire when the rate of growth of this function is $100,000. That's a pretty nice piece of change, nice coin, right? If this is spitting off $100,000 per year, yeah, why not, sit back and just let the money roll in and, travel the world, that kind of thing. All right. So what do we do with this again now? What do we do with this? We want the rate of growth to be $100,000 per year. This function right now is in terms of years. Set it equal. So we're putting 100,000 as the t, or are we setting it equal to 100,000? I want to be clear on that. All right, which one is it? Let's see what Adams is, or what Adam is saying. So the A prime, set it equal. Okay, good. Okay, so I'm going to put the 100,000 over here. Is equal to the million. The 1.05 to the power of t multiplied by the ln of 1. I don't really need that bracket for that. I don't know how to erase, so yeah, I don't know how to erase this thing here. So I'll put it in a bracket, 1.05. Okay, what's the next step? So I agree, but by the way, Adam and Sarah and the people who have said that's equal. So I said it's equal to 100,000. Walk me through the steps now. How do I solve for t? Okay, fine. How do I solve for t? And by the way, this is not just Adam. I can't have Adam carrying the load for the whole class. I need all of you to jump in here. Divide a million on both sides. Okay. And I think if I did that, I'd get 0.1. You can confirm that for yourself. So 1.05 to the power of t multiplied by the ln of 1.0. I keep using the bracket. I don't know why. So 1.05t times the ln of 1.05. I've done that, and I would assume that you'd accept that 100,000 divided by a million is 0.1. This is point on. Okay? What comes next? So I've done that. What do I do next? Come on, I'm waiting for some reaction from the class here, folks. What do I do next? I've taken Sarah's advice, and I got 0.1. 100,000 divided by a million is 0.1. Come on. Log to find t eventually, but is there another step before we get to that, Ashvan? All right, 0.1 is equal to 1.05 to the power of t times the ln of 1.05. One more step before we get to the logs. We'll get to logs eventually. Divide both sides. Thank you, Adam. Divide both sides by the ln of 1.05. So let me turn things around a little bit. Actually, I'll keep it as it is. So 0.1 divided by the ln of 1.05 is equal to 1.05 to the power of t. So far, so good, hopefully. All right. Now what? Adam is right. Right? Ashvan is right, but I wanted us to do one other thing first, which we've done. Know what's next. Right? Still haven't got an answer for James yet as to when he can finally decide that his $1 million lottery winnings is generating enough income for him to not have to work anymore. So we've done what Adam said. We've done what Sarah said. We've done all of that. What's my next step? Okay, log to find t. Good. Now, again, let me ask the question. Let me see if people were paying attention the first time I asked this. Which log should I use? Do I use a base e log, which is ln, the ln, or do I use a base 10 log? Which is the one that is going to make this answer? The ln, either one. Okay, good, good. So you are paying attention then. It doesn't matter, right? This ln in the equation does matter, right? So the ln that's in the equation, no, that has to be an ln, right? So this ln here, you can't use any log, any base for that. You got to use the ln for that. But it doesn't matter which one you're about to use. For the consistency's sake, we'll leave it as ln. Okay, fine, we can do that. We can do that. So I'm going to take the ln of the two sides of this equation, right? I'm going to take the ln of all of this, 0.1, over the ln already of 1.05 is equal to the ln of 1.05 to the power of t. And remember that we can put that t in the front, so it's t times the ln of 1.05 is equal to the ln of 0.1 over the ln again of 1.05. And obviously we can divide both sides now by the ln of 1.05. So here's what my final answer is going to look. Well, not the final answer yet, but here's my final calculation. The t is equal to the ln of this fraction, 0.1, over the ln of 1.05 over the ln of 1.05. Okay, over to you. Over to you. We decided to stick with ln all the way. I'd like to hear, no, you have to be very careful to use your calculator. You want to make sure you're using, if you have a fraction key, use a fraction key. I'd like to hear your answer for that now, please. All right, we need to, James is sitting on the edge of his seat, and he needs to know how many years does he have to wait until his investment is able to generate this $100,000 per year. All right, folks, over to you. Get your calculators out. Let's get that done. I'm waiting. I'm not going to do it myself. I'm asking you to do it. You all have calculators, or should. Why did you take the ln of both sides again so you can review this that quickly? I sure can. So when you are solving for an exponent, let me take you back to this part of the question where I'm pointing to right now. You can probably see the mouse. When you're solving for an exponent, actually from up here, when you're solving for an exponent, the only way to solve for an exponent, the tool that we have is to use logs. I'm taking the log of the two sides of the equation to solve for the exponent. Once I take the log of the two sides, then I can put that t, which is the exponent, in the front. That was that power law of logs, Taj. Does that, how many decimals? Oh, good. I'll answer that question in a minute. Okay, does that, okay, good. Give me 2 decimal places, please. If you have an answer there, Adam. Give me 2 decimal places. And I hope everybody else is doing this for themselves. Because if I give this question on a test, then there's nobody else there. Well, hopefully there's nobody else there doing it for you. Okay, Adam is about to, I think, about to give us an answer. But can you all be checking for yourselves and satisfying yourselves that his answer is correct? I can if you like. Okay. Yeah, sure. Go ahead, Adam. Give me 2 decimal places, please. And let's hear what everybody else thinks. Hopefully you're all doing this for yourself. 3.74. Not sure if I remember getting that. Yeah. The answer that I got, yeah. Yeah, I checked that again. Yeah, I checked that again because I remember doing this myself, and yes, I got an answer closer to what Richard and Ashfan and Vanessa and Jordan and Taj are getting, 14.71. Yeah, you probably should. You should probably try that. So 14.71. So tell me now, thank you, Sarah. Tell me now, what units would make sense for this answer? What units make sense for this answer? What units should I put for this t? It's years, absolutely. But we haven't answered the question for Adam yet, right? How old will he be when he retires? Well, not quite. You'd be pretty close, Sarah. You'd be pretty close. Um, because he's 25 now, add the 14.71 to the 25, and it's, yeah, 39 and change. So before this guy's 40 years old, right, he is going to be looking at his investment rolling in. And just let me just be clear about something. At that mark, at the 14.71 year mark, is when he hits the $100,000 per year. But the way compound interest works, in year 15 and 16 and 17 and 18, this is going to be more than $100,000 a year, right? This is when he hits the $100,000 a year, right? Now, clearly, hopefully everyone understands this. If I reduce the interest rate to, I don't know, 4%, 3%, 2%, or something like that, it's going, you missed two rounds. Okay, there you go. If you reduce the interest rate, well, hopefully it's obvious. If you reduce the interest rate, that's going to take him longer, right? If you increase the interest rate, which is unrealistic right now, let me just be totally honest with you. Interest rates are not that high right now, but if you increase the interest rates, then it's going to be even faster, right? And you can try this on your own time, right? A bigger interest rate means that your $100,000 per year is going to arrive earlier. A smaller interest rate means it's going to take longer. In fact, I remember trying it out, and I think if it was like 2%, which is actually not that far off. I'm sorry to disappoint you, but 2% is not that far. It worked out to be like 80 years, if I remember correctly. It was really a really long time. He'd be like 100 years old by the time it got to $100,000. But the fact is that interest rates are low right now. I mean, just to be very serious with you and sort of give you the core reality. Um, Interest alone is not going to make anybody rich right now, right? The good news, though, is that if you're borrowing money, interest rates on loans is also quite low. So that's actually good news. All right.